Good afternoon. Today we're going to be talking about section 2.4, infinite limits. So before this, we haven't really discussed anything involving the concept of infinity. And now we're going to bring in infinity little bit by little bit. So this first one, let's get started. So let's give a definition to infinite limits. Suppose a function f is defined for all values of x near a point a, that is to the left and to the right. If f of x grows arbitrarily large for all x sufficiently close to 8, we write the following and say that the limit of f of x as x approaches a is infinity. So what does this mean realistically? Well, let's take a look at a graph and a table at the same time. Oh, sorry, we'll do that in a moment. But we can also have negative infinite limits. So if f of x is negative, that is the function value is negative, and grows arbitrarily large in magnitude for all x sufficiently close to a, we write the following, and we say that the limit of f of x as x approaches a is negative infinity. In both cases, the limit does not exist. So infinity is a concept, not a number, which means it doesn't exist, right? We can't say, oh, this limit equals 8 or this limit equals 12. We say, well, the limit approaches infinity, so it does not exist. Now let's take a look at an example. So hopefully you can see this, it's big enough, but we've got this function 1 over x squared, and it's pretty easy to see that as we approach 0 from either side of our function line in black, followed by the line in blue, goes up, 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 and grows incredibly large towards positive infinity without bound. So we can see this in our graph. Let's see if we can prove it in the table. And the answer is, well, of course we can, because why would I give you an example that didn't work? So we can just plug in for our first value, f of 0.1. And in this case, because our graph is symmetric about y, we can plug in positive 0.1 or negative 0.1, and we're going to get the same answer out. So it looks like that, and that value is actually equal to 100. And you can check this by plugging in your calculator. So our first value is 100, and that's at 0.1. Now let's plug in f evaluated at 0.01. Well, again, we plug this into our calculator and we get 10,000. So we've got 10,000. And then finally, let's plug in for 0.001. And we're actually going to get out 1 million. And all these values can be found just plugging into your calculator. You can even use your phone or the Google calculator. You're going to get the same thing. I'm going to write a shorthand because I didn't leave myself enough space. But we can see that as we go closer and closer to the value 0, even as we do it a little bit by a little bit, our values for f of x, our function values, are going from 100 to 10,000 to 1 million to something even larger than that. So it's growing and growing and growing, and we can see pretty clearly from the graph, and we can see pretty clearly from the table that the limit as x approaches 0 of our function f of x equals infinity. And because infinity is a concept and not a number, equaling infinity means the limit does not exist. All right, let's take a look at another one to show that example of negative infinity. So here I have the graph of x over x squared minus 1 quantity squared. And I'm interested in what happens as we approach 1. Well, it's pretty easy to see that the limit as we approach positive 1 is over here. We follow this line. We approach positive infinity. And here I'm going to include the positive because it's pretty important. And then we're interested in, well, what goes on at negative 1? Well, as we follow our graph, we get into larger and larger negative numbers. So we go from negative 10 to negative 10,000 to negative 10 million, something like that. So that's to say that we approach negative infinity, which also does not exist. Now, finally, we have to talk about, well, we're approaching We're getting close and close and close to some idea of infinity when we go to take our limit. Does this have a name? And the answer is yes. And the name is a vertical asymptote. So the P is silent and it goes asymptote. So the P is silent, it's just all one word. You can practice it out loud and no one's gonna think you're being goofy. So we're talking about vertical asymptotes. And if the limit as x approaches a of f of x equals positive or negative infinity, the limit as x approaches a from the left or the x approaches a from the right equals positive or negative infinity, then the line where x equals a is called a vertical asymptote. So what does this look like? Let's go ahead and look at a graph. So here I've got a graph of the function x squared plus 1 over x plus 3 times x minus 1 quantity squared. And we can see that as we approach 1 from the right and from the left, we're going towards positive infinity. So let me, positive infinity. Again, as we approach -3 from the right, we're approaching positive infinity. And as we approach -3 from the left, we're approaching negative infinity. So the question is, what are these dashed lines called? Let me highlight them. What are these dashed lines called? And the answer is vertical asymptotes. And you can always find these on a graph because you can always see them. But what are some other ways to find them? And the answer is, let's look at just the denominator. So if I were to plug in -3 into my denominator, I would get a divide by 0 error, right? I wouldn't be able to do it because we can't divide by 0. So that gives me a signal in my mind that says, oh, as I approach -3 from the right and the left, something funky is going to happen. I'm going to blow up and approach one of the infinities. So that gives me a clue that the roots of my denominator are where vertical asymptotes live. So let me write that down. And that is all you need to know to close out section 2.3.